Welcome back, everybody. Today I'm going to be completing homework 3 part A for separations. And what we're going to be doing today is we're going to draw the schematics and derive the equations for the operating lines on a distillation column with a total condenser. We're going to figure out the schematics for the rectifying section, the stripping section, and the feed section. So I'm going to break this video up into each of the derivations so that we have enough room on the board for each one, but throughout them I'm going to keep the same schematic for our overall distillation column on the left here. So let's get started and draw a schematic for our overall distillation column of total condenser. So we got the main body of our column here. Of course, we've got a feed coming in, we're going to call F. And then coming out the top, we've got our vapor stream going into our total condenser, meaning that all vapor coming into here is condensed. No liquid is coming directly out, but coming out of our condenser, we've got our distillate stream and our reflux. We're going to call L, call this V. We've got our reflux coming out from our stream coming out of our condenser, going in, and above the feed, going up into that condenser, is going to be our rectifying section. And then moving on to below the feed, we're going to have our liquid coming out, L bar, or vapor coming back in, V bar, coming out of our reboiler. And then, of course, coming out of the reboiler, we're going to have our bottoms flow. In this section of our column, it's going to be our stripping section. Now we can go ahead and break this column up into parts and figure out the equations for the operating lines on each of these different segments. So let's go ahead and move on to doing our rectifying section. Okay, now that we've got our overall distillation column schematic here, let's go ahead and get into the details of the schematic for our rectifying section so that we can figure out the equation for the operating line within that rectifying section. So drawing out a similar kind of schematic here. We've got an overall drawing of the rectifying section. As we know, we've got V coming up and out of here into our condenser. And then coming out of our condenser, we've got our distillate and our reflux stream L. And within our rectifying section, we know that we have trays. Our trays or our stages going down, because we're going to count down for this from 1, 2, 3, all the way down to stage N. And then right below our stage N, our feed here, we've got our stage N plus 1. And then coming up out of N plus 1, we've got our vapor stream, V. Then coming down from stage N, we've got our liquid stream, L. This is our overall schematic for our rectifying section. We're going to need to draw a boundary around this so that we can figure out our equation for our operating line. So how we're going to look at this, we're going to consider V is coming in. And looking at this, we know that our V must equal what's coming out of here. So our V must equal our L plus RD. As with our boundary we've drawn, only our distillate flow and our liquid flow are coming out, and only our vapor flow is what's coming into the system. Furthermore, we know that the vapor composition of more volatile component yn+1 at stage n+1 times V must equal our xn, our liquid composition of the more volatile component at stage n, times our L plus our xd, our liquid composition of our distillate flow, times our distillate flow d. And then substituting in this equation in for our V here, we can get that yn+1 times L plus D is going to equal xn times L plus xd times d. And then isolating our yn+1, we get the expression yn+1 equals xn times L over L plus D plus xd times d over L plus d. And moving on from here, we're going to need to substitute in a very useful metric called our reflux ratio, R, which equals L divided by D. And subbing this into this expression, we get that yn+1 equals xn. Make sure I don't mess up my algebra here. So we've got plugging in I believe this gives us R over R plus 1 plus xd times 1 over R plus 1. And plugging that in, just making sure I did all my algebra right here. That's all right. So here, we've got our governing equation for the operating line for our rectifying section, as well as our schematic for our overall rectifying section. So moving on from here, I'm going to erase all this to give us a little more room for our stripping section. We're going to also derive the schematics and a similar governing equation for the operating line for our stripping section. So let's go ahead and move on to that. So now we derive our operating line equation and our schematics for our rectifying section. Let's go ahead and move on to our stripping section. So similar to our rectifying section, we've got our general body, of course. With our tray n, our tray n plus 1, and then any amount of additional trays below these stages. Our feed, and then we've got our vapor coming up, n plus 1, and our liquid coming down from stage n. But now we're looking at the stripping section. We're going to call this V bar and L bar. And then going down to the bottom of our stripping section, we've still got our L bar and V bar boiling up from our reboiler this time. And then, of course, you got our bottom slope. And similar to what we did before, I'm going to go ahead and draw our boundary here, excluding our feed. So, all around here. And as you can see, yet again, all that we have entering and exiting this boundary is our V bar, our L bar, and our bottom slope B. So this time around, we can say that L bar must equal V bar plus our bottom speed B, as only L bar is coming in and only V bar and B, our bottom slope, are leaving. And similar to what we did before, we know that our xn times our L bar is going to equal yn plus 1 times our V bar plus xb times our bottom slope. Because yet again, similar to the condenser, it's all liquid coming out of the condenser, it is all liquid coming out of our bottom slope. So again, as we did previously, I'm going to go ahead and plug in our first equation into our second equation. We're going to get that our xn times V bar plus B is going to equal yn plus 1 times V bar plus xb times our bottom slope. And then, as we did before, I'm going to isolate our yn plus 1. So, you can say that yn plus 1 is going to equal, doing a lot of algebra in my head here, so hopefully I don't make any mistakes. X equal xn times V bar plus B over V bar minus xb times B over V bar. And this time, we are going to sub in our boil-up ratio. Our VB equals our V bar over B. And subbing that in to our overall expression, we get that yn plus 1 equals xn. Think this through. B plus BB plus 1 over VB, as we're multiplying out that 1 over B minus xb times over B. That right there is our equation for operating line for our stripping section. Moving on from here, we're going to do our final schematic for our feed section. We are going to derive the governing equation. feed section to finish out this video. So let's go ahead and move on to that part. Now that we've found our operating line equations for our rectifying and our stripping section, we can do our last section, which of course is going to be our feed section. And drawing the schematics for this, we know our previous derivations. We've got our inlet flow feed F. Coming on in, we've got our liquid flow coming from the rectifying section, which is our L. Vapor flow coming out of the feed stage, V, up into our rectifying section. And then we're flowing down L bar into our stripping section, and coming up we've got V bar coming up from our stripping section. So in order to find the operating line equation for our feed section, we're going to take a look at some of the earlier equations we derived for our rectifying and stripping sections. So as we said earlier, we know that for our rectifying section, we know that yn plus 1 times V is going to equal our xn times our liquid stream L plus our xd times our distillate stream D. And then for our stripping section, we can recall that our xn times our L bar this time is going to equal our yn plus 1 times our V bar plus our xb times our bottoms flow B. What we're pretty much going to do with these two equations is we're just going to add them together. So after adding them together and rearranging a little bit, what we're going to get is that yn plus 1 times our V minus V bar is going to equal xn times L minus L bar plus xd times D plus xb times B, our bottom's flow. And looking at these two expressions, we know if we look at like an overall boundary of our entire column, all we've got coming in and out is our distillate and our bottoms, and all we've got coming in is our inlet flow rate F. So we can say that these two expressions are just equal to our ZF composition in our feed times our feed flow F. So moving on from here, as we did in the previous two sections, we're going to need another metric, which is going to be our Q. And our Q is it's the liquid fraction of our feed stream. So knowing that, we can say that V minus V bar is just going to equal 1 minus Q, i.e. the fraction of the feed stream that's not liquid, times F. The other side of that, we can say that L minus L bar is going to equal our Q times our feed stream F. And subbing these two into our equation up here, we get that yn plus 1 times 1 minus Q F is going to equal xn Q F plus Z F times F. As you can see, we've got our inlet flow F, our feed flow, all across here. So we can just go ahead and eliminate that from each of these. And then, if we isolate our yn plus 1 as we've done previously, we get our governing equation for our feed section, our yn plus 1 equals xn times q over 1 minus q plus zf times 1 over 1 minus q. That right there is our governing equation for our feet section of our column. I believe that finishes out our video, as we've got our operating line for our rectifying, our stripping, and our feed section. And we've gone ahead and drawn the schematics for all three of them in the separate parts of this video. So I will see you in part B.